All right, so let's take a look at section 8.5. Okay, it's same section in your book, part 3. It's a very large section. Okay, we're pretty much spending the entire week in section 8.5 in your text. Or if you're looking stuff up, you can also find it in the packet under dot product. All right, so what I've written up there is basically two vectors in unit vector form. The coefficient of I is A1 for vector V. The coefficient of J is B1. And then for vector W, the coefficient of I is A2, and the coefficient of J is B2. Okay, those would all be numbers, like 3I plus 7J and negative 8I plus 12J. Okay. So A1, B1, A2, and B2, those are all numbers. Okay, so we're going to define what the dot product is. So far, the operations we've defined with vectors are addition. What do you get when you add a vector to another vector? The type of answer you get is a what? Yep, Sylvia?
A new vector.
A new vector. Okay, so when you add vectors, you get a vector. When you subtract vectors, well, that's the same as adding, just adding the opposite. So that's subtracting vectors, you get a new vector. When you scale a vector, you get a new vector. This one's going to be a little different. Okay? When you multiply vectors using a dot product, let's see if you can tell me what kind of answer I'm going to get based on that. So remember, A1 and A2 are numbers, and B1 and B2 are also just numbers. So if I multiply A1 and A2, and then add B1 times B2, what kind of answer would that be? Would that be a vector? Sam?
Would that just be a magnitude?
It's just, it's actually not a magnitude, but it is a number. It's not a length of anything necessarily, but it is just a number. Now there's another way we can multiply vectors, and that's with a cross product. We can't do cross product yet because cross product only applies to 3D vectors, okay, which we'll do tomorrow. But if we have some time, we'll talk a little bit about cross product. Okay, but today we're going to focus on dot product. Right, so our first example is I want to find V dot W. Okay, and you have to say it V dot W. You can't say V times W. Because somebody who knows about vectors, they'd say, well, how do you want me to times them together? Do you want me to times them with a dot product or times them with a cross product? It makes a difference. All right, so we want to find V dot W. Okay, so basically, take your components of I, okay, multiply them together. Take the components of J, multiply them together, and then add those two answers up. And that's the dot product. Okay, so Andrew, what are the first two numbers I'm going to multiply together?
2 and 5.
Yep. So we did 2 times 5 plus Sylvia.
Oh, 3 times 3. Negative 3 times.
Negative 3 times 3. So we do that out. Justin, what's my dot product going to be when I do that out?
10 minus 9.
Yep. 1. Okay, so there's my dot product. Okay, later on, we'll explain what you can use the dot product for. Okay, we can use it specifically for finding an angle between two vectors. But for now, we're just going to practice finding the dot product. Okay, so that's V dot W. Okay, let's try to switch it now and find W dot V. So, Carly, what would be the first two numbers I multiply if I'm finding W dot V?
5 times 2.
Yep, I do 5 times 2 plus.
And then 3,
Yeah, go ahead.
3 times negative 3.
And then 3 times negative 3. Right, so Cassie, what's going to be the dot product there?
1.
It's still 1. So what does that mean about the dot product? There's a word I'm looking for to describe what just happened. Yeah?
Optimization.
Okay, so yeah, you think along the right lines. That's a statement we usually use for logic, like a biconditional, like if then, and then switching the converse, finding that. But we're on the right idea of switching something and having it still be true. Does anyone know what that's called? It's commutative. Okay, so the dot product is commutative. Good. Okay. When we talk about cross product tomorrow, that is not commutative. Okay, so that might be one of the first times in math you've seen multiplication, and when you change the order you do it in, it changes your answer. Okay. That also happens with matrix multiplication. If you take two matrices and multiply them, and then switch their order, assuming you can still multiply them because there's certain conditions that have to be met, the answer is not the same. Okay. But for dot product, it is commutative. Okay. Okay, let's take same vector we just had and find v dot v. In other words, you're dotting vector v with itself. Sam, what would I multiply together to find v dot v?
2 times 2.
Yep.
-3 times -3.
-3 times -3. So that's going to give me 4 plus 9, or 13. Okay. And let's also find w dot w. All right, so Josh, what's w dot w?
5 times 5 plus 3 times 3.
Yep, 5 times 5 plus 3 times 3. So that gives me 25 plus 9, or 34. What's another way of saying 5 times 5? 5 squared. And 3 times 3? 3 squared. Does anybody recognize what this is similar to doing, but not quite? There's one step missing from it. Take 5 squared. Let's go look at w. Take the 5 and square it, take the 3 and square it, add them up, and then we stopped. But yesterday we did one more step, and it gave us the blank of the vector. Yeah? The magnitude. Okay. So if you take the 5 and square it, take the 3 and square it, add them up, you're almost finding the magnitude. The last step would be to take the square root. We just didn't do that. So, if you take the dot product of a vector with itself, you don't get the magnitude because you haven't taken the square root, but you get the magnitude squared. All right? So if I went back to the previous problems, if I took 13 and now took the square root of it, that would be the length of vector v. If I took the square root of 34, that would be the length of w. But if I don't take the square root, the dot product of a vector with itself is equal to the magnitude squared. Okay, that's going to be important. Okay, we're going to combine that idea with the law of cosines in a few minutes. Okay, and it's also true for w dot w, any vector dotted with itself. Okay, any question on that idea? Dotting a vector with itself gives you the magnitude of the vector squared. All right. Okay, let's do this one. This time it's not written with i's and j's. It's using the other notation, but that's fine. We still do the same idea. Okay, Orlando, what would I multiply here to do my dot product?
2 and 0.
Yep.
And 6 and 0.
Okay. Anything else I need in there?
Addition.
Yep. I need addition. Okay, and Brian, what do I get when I do that?
0.
0. What is this 0? What type of answer is it? So when you find a dot product, your answer, I think someone said this earlier, it's always what? In terms of like the type, like when you add, here's another example. When you add two vectors together, what kind of answer do you get? a resultant what?
Vector.
Vector, exactly. So when you add two vectors, you get a vector. When you do a dot product, your answer, it's not a vector, it's just a help him out. What is this thing here? Yeah, it's a number. Okay, it's a number. Versus if I gave you a problem like this, 2, 6, and I said to add to it the vector -2, -6, and you wrote this as the answer, I'd mark it wrong. You'd have to write, that is the answer. Okay? So when you add vectors, the answer you get is a vector. In this case, it would be the 0 vector. When you do a dot product, the answer is always a number. In this case, the 0 number. Any question on the difference between 0 number, 0 vector? Could also do the 0 in bold. Okay, that's how your book would do it. Okay, but just keep that idea in mind. Difference between 0 as a vector and a number. Dot product, always a number. Okay, the dot product is distributive. Okay, so if you have a vector on the outside and you're dotting it with a sum or difference of vectors in parentheses, you can distribute it as u dot v plus u dot w. All right. And one thing that we can use the dot product for that's kind of leads us into an application is to find an angle between two vectors. All right, so we're going to go through and see if we can figure out what the formula is. Okay, so on the next page, I'm going to draw two vectors. And I want a formula for theta, to figure out theta. Well, first thing I need to figure out is what that would be. Okay, and that's a little tricky to figure out. Does anybody see what that vector in black would be? It's a combination of u and v somehow. Yeah?
Well, could we use the Law of Cosines?
Well, first thing is I just want to represent the vector in black. So until I have a label for each side, and this is going to be side angle side, so we're going to use Law of Cosines to do it. But so that's a good thought. We just need a label for that side in black first. How could you combine u and v and get what's in black? Yep.
Question, why couldn't you just, because you know each endpoint of u and v, why couldn't you just find a distance between the terminal points?
Okay, what would you do with that?
You use the distance formula.
Okay, so you could use the distance formula. You could find the length of each vector.
Well,
Yep.
no, like, couldn't you, because from that you can see where u and v both end, so you know each of those points, and so you could just find the distance between the points, couldn't you?
To find the length of u and the length of v?
No, to find the length of the last side.
Oh, I don't need the length of it.
Oh, okay.
So ultimately, all I'm going to care about is what this angle is. There's all kinds of things you could do to get it. If you know u and v, you could find the length of u. You could find the length of v. Then you could use the distance formula again and have a side-side-side triangle, which would be Law of Cosines. But we're going to come up with an even faster way, because it's going to take too long to find the length of three vectors, then plug it all into the Law of Cosines, simplify it, and then get the angle. We're going to come up with a formula that can do it all in like 2 steps, without ever finding the lengths of all the sides. Okay, but let's see how we could write that vector in black as a combination of u and v. What's one thing I could try? What's one way you could combine vectors u and v and get a new vector? Yeah? We could try adding them. Right, so let's off to the side. Let's take u. Let's make a copy of it. take V, and let's add it on the right way and see if we connect them. Do we get the one in black? Okay, that's what I get when I take U plus V. Is that the same as the one I had in black? No. But that's a good guess. We could try U plus V. What else could we try besides U plus V? How about V plus U? Michael, you think that would it make sense to try V plus U?
No,
No, why not?
because you get the same answer.
You're going to get the same answer. It's commutative. So it doesn't matter if you try U plus V or V plus U. Okay, what's another way we could combine them and maybe hope that something works out? Michael?
Try subtracting them.
Yeah, what do you want to try?
U minus V.
Let's try that and see what happens. So we've got, that's U. Let's take V. And remember to subtract V, we're going to flip it around the other way. So it's basically rotating it 180 degrees or reflecting it twice. Okay, so there's U. There's V. Let's connect them. Do I get the one that's in black? No. Yeah. Maybe not exact because I didn't use my ruler, but pretty close. Right, so that vector in black is U minus V. Now we have a label for each side. Okay, next I want to set up the law of cosines. Okay, using this, think of it as a triangle. Okay, remember, law of cosines says one side squared equals the sum of the other two squared. And you know what, let's start with that. So I want the length of U minus V squared equals the length of U squared plus the length of V squared. Minus, anyone remember what number comes next in the law of cosines here? Minus, yep, 2 times what? Perfect. Times the length of U times the length of V times the cosine of the angle that's across from the side I started with. In this case, theta. Okay, so there's the law of cosines. Just plugging everything in that triangle into it. All right. Now, for now, we're just going to leave this off to the side. We're going to come back to this part. I want to work with this other side. The magnitude of a vector squared. There's a way we can rewrite that based on something we just did earlier with dot product. How can you rewrite the magnitude of a vector squared using dot product somehow? Yeah?
Well, we were saying that V dot V is the same as the magnitude of V squared.
Mm-hmm.
And we were also saying that W dot W is the same as the magnitude of W squared.
Yep.
So couldn't you do the same thing? Just dot product them and then subtract their product?
So what would you put on it for each?
Magnitude of U squared dot V squared.
So remember the formula says that whatever's inside here, okay, whatever vector is inside those double bars, that's what you're using for the dot product. Okay, so if it's a V, it's a V dot V. If it's a W, it's a W dot W. If it's a triangle, it's triangle dot triangle. Okay, whatever's in there, that's what you put as the dot product. So what would be in each of these? Yeah,
U minus.
U minus V. So if you take the vector U minus V, which is the one in black, and dot it with itself, you'll get the magnitude of that vector squared. Okay, now we're going to do out that right-hand side. We're going to distribute. Okay, we're going to do the double distributive property. Just remember, it's all with dot products. So we get u dot u. We get u dot negative v. So I'm going to write it as minus u dot v. We get another minus u dot v. And then we get a negative v dot negative v. That's a positive v dot v. Okay, any question on that? All right, now I want to simplify what I can here. What is u dot u? What would that come out to?
U squared?
Not quite. We're going to use that formula we had from earlier on. We actually just used it in reverse. Now we're going to use it the other way right here. Yep.
The magnitude of u squared.
Yes, the magnitude of u squared minus. Now, u dot v, I can't really change that to magnitude, but I can combine them. I have a minus u dot v and a minus u dot v. Brandon, what would that combine to?
Negative 2 u dot v.
Yeah, you have 2 of the u dot v's, and they're negative. Okay, and the last part, v dot v. Yeah,
The magnitude of v squared.
that's the magnitude of v squared. Good. This is the left-hand side of that equation. And up in red, I have the right-hand side. What's in the 2 red boxes are equal. All we did was take the left-hand side and rewrite it a little bit. Now I'm going to set the left-hand side equal to the right-hand side using what's in those 2 boxes. And I want you to see what happens. So our left-hand side is magnitude of u, 2u dot v, plus magnitude of v squared equals magnitude of u squared plus magnitude of v squared minus 2 magnitude u magnitude v cosine theta. Hey, anybody see something I can do here to simplify that equation? Well, let's try to get all the like terms on the same side and watch what happens when you do that. Yeah, Sylvia?
Can you subtract u squared from both sides?
Magnitude of u squared?
Yeah.
Yep. What's going to happen if you subtract that from both sides?
So
Cancels out where?
both sides?
On both sides. They both have magnitude of u squared, so if you subtract it from each side, it cancels out. Okay? Anything else we can do?
Same thing with magnitude of v squared.
Yep. If you subtract magnitude of v squared, that cancels out from both sides. So now we're left with negative 2 u dot v equals negative 2 magnitude u magnitude v times cosine theta. Okay, now my last step, the way they usually write this formula is they get cosine theta by itself. Okay, so how would I move everything that's left away from cosine theta to the other side? Yeah, I would divide. Divide by that number in front of cosine. So divide by negative 2 times the magnitude u, magnitude v, That cancels. And divide by -2, magnitude u, magnitude v. Now before I write my final answer, is there anything else I could cancel on the left-hand side? Yeah.
-2.
Yep, the -2's. So, all that you end up with is the dot product of two vectors divided by the product of their magnitudes. That's equal to the cosine of the angle. So it gives us a very, very simple formula based on the law of cosines to find the angle between two vectors. All you need to find is their dot product and the product of their magnitudes. And divide them. That's it. Okay. And then to get cosine by itself, we'll use inverse cosine on each side. Okay. So any question on that formula?
Is there a name for it?
No specific name. It's just the formula to find the angle between two vectors.
Okay.
That's it. So any question on that? So this formula is going to be quite a bit shorter than using the law of cosines, but you could. Okay, as Andrew said earlier, you could find the length of each side of your vector in your triangle, use the law of cosines, and get the angle. But you're really reinventing this formula every time you're doing that. Okay? And you saw all the things that canceled out. You're finding a lot of things with the law of cosines that are just going to cancel out. You don't need them anyway. So just use the shortcut. All right, so here's two vectors. Let's find the angle between them. Okay, so there's three things you need. You need the dot product, the length of u, and the length of v. Okay, let's start with our dot product. Okay, so Nick, what would be my first two numbers I multiply for the dot product of u and v?
4 and 2.
Yep, 4 and 2. Okay, let's sign the next two. -3 and 5. So Shannon, that's going to give me a dot product of what? Yep, -7. Okay, so that's one thing. We got our dot product. Now we need the length of u. Okay, so Brandon, I'm going to start with that square root. And what's my first step to find the length of u?
Square 4.
Yep.
-3.
4 squared plus -3 squared. Okay, Marina, if I add those up, 4 squared is 16, -3 squared is 9. What's 16 and 9?
25.
25. Okay, so that's the second thing I need, the length of u. And Julia, can you give me my formula to find the length of v?
2 squared, or squared, 2 squared, plus half squared.
All right, and Tiara, when you add that up, you get 4 plus 25 gives me square root of 29. Can we reduce that? No. You can check if 4 goes into it, 9 or 16. Okay, none of those go into it, so we just leave it. Okay, now plug everything into the formula we just had. Where was it? Right there. Cosine of your angle is the dot product over the product of the magnitudes. There it is. So my dot product is -7 over the product of the magnitudes is 5 root 29. And Andrew, how am I going to get theta alone?
Is the inverse cosine.
Good.
The other side.
So do inverse cosine on each side. and see what it comes out to. All right, so take the inverse cosine and do this in degrees. Okay, don't bother with radians. Divided by 5 square root 29. Okay, you should be able to type it all in at once. Let's try that. And if, yeah, that was a problem. Let's put parentheses around the denominator so it does that first. Okay, so now it'll do 5 times the square root of 29 first. Then it's going to do -7 divide by that. And now it'll work okay. That's correct. So 105.07. That's the angle between those two vectors. All right, any question on that? So that's how you find the angle between two vectors. All right, sometimes there's a couple special things that can happen when you find the angle. Two vectors might be perpendicular. Okay, that's a special case. If they're perpendicular, what does that mean the angle between them is? 90 degrees. Okay, so if the angle between them is 90 degrees, we say that that's perpendicular. Okay. Or another word for that they often use with vectors is orthogonal. Okay. Orthogonal just means that two vectors are perpendicular. Just another word for it. Okay, so I want to see what would happen if two vectors are perpendicular or orthogonal. Okay, in terms of solving for it in that formula. So we just said that that means the angle is 90 degrees. So we have the cosine. The angle would come out to 90. You'd have the dot product in the top of something, whatever it happened to be, and you'd have the product of the magnitudes in the bottom. Okay, so it would be the dot product over the product of the magnitudes. What does the cosine of 90 come out to? 0. 0 would equal that fraction, whatever the dot product is and whatever the product of the magnitudes is. What's the only way that that fraction could come out to 0? Because it's going to come out to 0 if they're perpendicular, and that can only happen if.
The numerator is 0?
And what's in the numerator?
The dot product?
The dot product. So there's a shortcut there. When two vectors are perpendicular, if their dot product comes out to 0, you're done. There's nothing else you even need to do. It doesn't matter how long they are. 0 divided by anything is going to be 0. And then if you take the inverse cosine of 0, you get 90. Okay, so that's a shortcut you can use when two vectors are perpendicular or orthogonal. Their dot product is 0. If you just want to know the angle in general and it's not something special, you've got to go through the whole problem. But if they are perpendicular, this is a nice shortcut. Okay, so this is basically like a true-false. Okay? I want to know, are the vectors perpendicular? So find the dot product. If it comes out to 0, they're perpendicular. If it doesn't, they're not. Okay, so Sylvia, what would I multiply to do my dot product here?
It would be 2 and 1.
Yep, 2 times 1.
And 1 and 2.
1 and 2. What does that dot product come out to?
4.
4. Are these vectors perpendicular?
What?
Are these vectors perpendicular?
No.
No. What would the dot product had to have come out if they were perpendicular?
0.
It would have come out to 0. Okay. So these are not perpendicular. Yep.
Wait, wouldn't you be able to tell just by looking at two values because wouldn't it only come out to 0 if one of them was missing either the I value or the j value?
Well, I mean, you could have like 3 and 5 and then -3 and 5.
Ah.
So something like that. If you just make any one of those 4 numbers negative, now they're perpendicular. Doesn't matter which one you do. But you put a negative in front of any one of those 4 and you'll make them perpendicular. Or you could also have, you could have a 0 for one component, and then a negative 1. And actually, no, if you had a 0, yeah, if you had a 0 for one component, like say the I, then in the other one you'd have to have a 0 in the j component. Like if this was 0 and 0, now you'd have 0 times 1 plus 1 times 0. Those would be perpendicular. One of them would basically be horizontal, one of them would be vertical. Yep. All right, so that's the case where they're perpendicular. The other one is parallel. What would the angle be between 2 vectors if they are parallel? Yeah?
180.
Okay, you could have 180, which would basically mean one vector like this, one vector like that. That's a 180-degree angle between them. What else?
It could be 0.
It could also be 0. Basically, if you had something like this. 2 vectors pointing in the same direction would be parallel. Or if you have 2 vectors pointing in opposite directions, those are also parallel. Okay, you can think of it like that. However you want to think of it. All right, so let's see if there's any kind of shortcut with that. Let's check 0 first. So it would be dot product over the product of the magnitudes. What's the cosine of 0? Yeah, it's 1. How can a fraction equal 1? How does that happen? Yep.
If the numerator and denominator are the same.
Great. So if the numerator and denominator are the same, your vectors are parallel. In other words, if the dot product is equal to the product of the magnitudes, you still have to find both, though. There's no shortcut. But if they come out equal, you get 1. Okay. Now, the other angle we said was 180. What's the cosine of 180? Yeah? -1. So if there's an angle of 180 degrees between them, somehow this fraction is going to come out to -1. Okay, Lisan, how can a fraction come out to -1?
If that was negative, the numerator denominator, and they're the same.
Right. Well, can you say that again?
If the numerator and denominator are the same, but one of them is negative.
All right. So yeah, why don't we say if they're opposites?
Yeah.
Yeah. So if one of them, basically the way she said it, if the numbers are the same but one of them has a negative in front, or if they just come out opposite. All right. So if your numerator and denominator come out opposites, they are also parallel. Usually I'm not going to ask you to distinguish between are they parallel because the angle is 0 or are they parallel because the angle is 180. Usually I just care, are they parallel or not? All right. So let's determine if those 2 vectors are parallel. Okay, so we're hoping for the dot product to either come out the same as the product of the magnitudes or opposite. One of those 2 things. Okay, Taylor, what would be my dot product? How would I find it?
You're going to multiply the 4 and the 2 and add,
Yep, 4 times the what?
I'll just say 20.
20? Okay.
And then add -5 times the
-5 times -25. Okay, so 4 times 20 gives me 80. -5 times -25, that's 125. And if I add those up, what's 80 plus 125? Go ahead, yeah.
205.
Yep, 205. Okay, so I got my dot product. Okay, Michael, how would I get the length of V?
4 squared plus
Good. 4 squared plus negative 5 squared. And that would be the square root of what?
41.
Yep, 16 plus 25 is 41. And the last thing I need is this, the length of W. Okay, so we got 20 squared plus negative 25 squared. That's going to give me 400 plus 625, or 1,000, square root of 1,025. Now, you might be able to simplify 1,025, the square root, but it's not important. We're just trying to find out if these vectors are parallel or not. This is not a final answer. So don't worry about cleaning it up. All right. So we've got the dot product over the product of the magnitudes. Okay, let's see what the denominator comes out to. If they're parallel, what are we hoping it comes out to? 205 or negative 205. Okay, one of those two. In this case, it's obviously a positive times a positive, so it's not going to be negative in this case. Okay, so square root of 41 times square root 1,025, we get 205. So at this point, we can say they're parallel, because the cosine is going to come out to 1. Inverse cosine of 1 is 0. Okay, so the angle between them is 0. So yes, they are parallel. Okay, so any question on those two special cases? They come out perpendicular or parallel? So our last one, this will be the, I think this will be the only word problem we do today. This is going to be about an airplane, okay, flying, and it's going to encounter a jet stream, a wind. It's going to blow it off course. And I want to find out how much off course it's going to blow. Okay. So the wind, when it hits the plane, can do two things to it. One, it can change the speed of it, depending on if it's a headwind or a tailwind. And it can also change the direction of it. And so you're going to think of the wind as a vector. It has a speed and a direction to it. The plane also has a speed and direction to it. And we're going to combine the two and get a resultant force. Okay, so the Boeing 737 is maintaining an airspeed of 500 miles an hour south. Does everyone understand the difference between airspeed and ground speed for an airplane? All right, so the airspeed and the ground speed can be different. All right, so here's an example. You're driving in your car. Okay, let's say you're on the highway and you're going 60 miles an hour, and you're driving into a wind that's also 60 miles an hour. If you put your hand out the window, the air hitting your hand is going to feel like it's going how fast? If you're driving 60 and you're driving into a headwind, 60 miles an hour. Yeah. The wind is going to feel like it's hitting your hand at 120 miles an hour. Because if you were just standing still, not moving, it would feel like it's hitting you at 60. And then if you're driving 60 into it, it's going to hit your hand even faster. Now, if there was a cop on the side of the road and he used his radar gun, how fast would it say you were really driving, though? You're driving 60, even though the wind is hitting your hand at 120. Okay? That's kind of the difference between airspeed and ground speed. Okay? The airspeed would basically be, if you put your hand out of the plane, it wouldn't do it. If you put your hand out the plane, how fast is the wind hitting your hand? Okay? The ground speed, if somebody had a radar gun and pointed at the plane and got the speed of it, how fast is the plane actually moving from the ground? Okay? Any questions? Does that make sense? Okay. So in this case, the jet stream is blowing 80 miles per hour in a northeast direction. Okay, when you read about the direction of the wind, you have to read if it says it's blowing towards a direction or from a direction. Okay? If it's blowing in a northeast direction, it's coming from the southwest. So the wind is coming from the southwest, blowing towards the northeast. Right? If in a problem it said the wind is coming from the south, that would mean it's blowing north. It's coming from the south, blowing north. If it's coming from the west, it's blowing east. It's from the west towards the east. I want to find the actual speed and direction of the plane relative to the ground. Right, so what we'll do is we'll make a picture, and let's just try to figure out if the jet stream is helping the plane or is it hurting the plane. All right, if it's a headwind, it means it's flying into it, it's slowing it down. Generally, when you fly from like Europe to the United States, it takes longer. Yeah, it takes longer because you're flying into the wind. If you fly from the United States to Europe, it's faster because you're flying with the wind. And that also affects the fuel and all kinds of things the plane would use, but we're not getting into that. Okay, so the first thing is we have a plane that's maintaining an airspeed of 500 miles an hour south. Okay. So let's sketch that. Okay, so on our grid, why don't we set it up, let's see. Let's set it up in units of 50. Okay, and I think that should be good enough. Okay, right on the edge of our graph. If we need to adjust it, we can. That should be okay. Bless you. Okay, so 500 miles per hour south. Okay, which direction is south? That's important. Yeah.
Down.
Yeah, from a perspective like this, south would be down. Okay, so that's going to be the vector for the plane. Like that. Okay. And now we have a wind blowing 80 miles per hour northeast. Okay, which quadrant would that be in? Northeast. Yeah.
Upper right one.
Yeah.
That's good.
Yep. Quadrant 1. Okay, so there's your directions, just in case anybody needs those. That's east. All right, and it's blowing 80 miles per hour northeast. All right, so let's sketch that. Okay, so I'm going to sketch that from the origin. And 80 miles an hour, well, might be something about like that. Just guessing. Okay, it'd be a little bit shorter if you did it horizontally than 2 grid lines. Okay, 2 grid lines would be 100. Okay, it doesn't have to be exactly to scale. Okay, so it might be a little shorter. Okay, now let's do that in green. Okay, so let's label each one. Okay, so in red, this is my plane. In green, that's the wind. So is the wind helping the plane here, or is it working against it? What do you think?
Working against it?
Yeah, the wind is blowing up and to the right. Okay, the plane is trying to fly south, so it's hitting the plane on its side a little bit. blowing it upward. So it's definitely not helping. All right, so our first goal is to figure out a velocity vector for each of those things. One for the plane, one for the wind. Okay, let's start with the velocity vector for the plane. Okay, so remember your velocity vector is the magnitude times the cosine of your angle, that's the horizontal, and then the sine of the angle is the vertical. What's the magnitude? How fast is the plane going? Yep, 500. Now we want to think of the angle the plane is flying at. Okay. What's the angle? And this is confusing. Don't think of it in terms of a compass, which is a little different. Think of it in terms of how we normally do angles. What angle is straight down? 270. So cosine 270. Okay, that's the horizontal component. Well, if the plane is flying straight down, hopefully the horizontal component comes out to 0. Shouldn't be 1 for the plane. Okay, plus sine 270 j. Okay, and distribute. So we take the cosine of 270. Sure enough, we do get 0 times 500. So there's no horizontal component for the plane. Straight down. Plus, take sine of 270. Comes out to -1. So actually, I'll make that a minus. So that's minus 500j. Okay, the minus just means that the vertical component is down, not up. Okay, it's down. There's your velocity vector for the plane. If you don't want to write 0i, you don't need it, but just so people can see each component, I wrote them both. Okay. Any question on that? All right, now we need the velocity vector for the wind. Okay, what was the speed the wind was blowing at? Yeah, 80 miles an hour. Now I need the angle it's blowing at. So if we look back at the problem, it said it's blowing northeast. Let's assume exactly northeast. So if it's blowing exactly northeast, what would be the angle to the positive x-axis? Just like we did with the plane. That was 270. What's that part? So 45 degrees. Yep. Okay, now in this case, neither component is going to come out to 0, and it shouldn't, because there's an up component and a right component. But the two components should come out what if you compare them to each other? They should come out the same. On a 45-degree angle, it's exactly as much up as it is to the right. Okay, so let's do it out. Really, we just need to do it out for the first part. Cosine 45 times 80. So the plane is being blown basically 56.57 miles per hour to the right. And it's also being blown 56.57 miles per hour up. If you take sine 45 times 80, that's what you'll get. Okay, so there's our velocity vector for the wind. Now we're going to combine the two. And when we combine them, that's going to give us the actual vector the plane is flying on. All right, so it's the velocity vector actual for plane, taking into account the wind. All right, so we've got 0 plus 56.57i. Okay, that's its horizontal component. And it's trying to fly down at 500 miles per hour, or south. But the wind is going to slow it down 56.57. So it's really only flying at 443.43 south. Okay, so that's the velocity vector for the plane, taking into account the wind. Okay, now the question is, find the speed of the plane and the direction. Well, let's find the speed. So the speed of the plane would be the what of this vector? Yeah?
Magnitude?
Its magnitude. So find the magnitude of this vector, and that'll tell you if somebody was standing on the ground with a radar gun, how fast it's actually going. So let's write it like this. So the magnitude of V, we'll just call it actual. Okay, so it's 56.57 squared plus negative 443.43 squared. Any question on setting that up? And this will tell us how fast the plane is really going. So again, it's not going to be going quite as fast as they thought, because the wind is going to slow it down a little bit. So 56.57 squared plus 443.43 squared, and take the square root of that answer. So from the perspective of the ground, okay, the plane is traveling at 447.02 miles per hour. Okay, any question on that? That's the speed that it's traveling at. Okay, what's its actual direction? Well, the way you could visualize it, add these two vectors together like this. That line in black represents the actual magnitude and direction of the plane. So it's being blown off course to the east a little bit. Okay, how you describe that angle? Well, there's many ways you could do it. Okay, what I would probably do is take the velocity vector for the plane and take this one in black. This is the actual. Okay, we already know what it is. Find the dot product between the red one and the black one. That'll allow you to find the angle between the two. So get the angle between the red and the black vector. And let's say the angle comes out to, I'm just going to make this up, 6 degrees. You could say the plane is being blown off 6 degrees off course from flying due south. Okay, that's one way to say it. Or you could also say the plane would be flying, in terms of our directions, at 276 degrees. Okay? 270 would be straight down, but it's 6 degrees past 270, so it's at 276. You could say it that way too. Real compass headings it's a little confusing because they don't use the same system we do. We do east as 0. On a compass, east is really 90. So don't worry about what the actual compass heading would be. That'll get confusing. Okay, any question how you'd finish that up? Just find the dot product between the red and the black, get that angle, and then describe it however you want. But you just need the dot product and use the formula. Okay. So that's our resultant force problem. Okay, combining two forces together and finding a new force or new direction. All right, so the homework is on 352. Okay, it's 7 to 17 odd. Okay, make sure you read the directions carefully. Each question has 3 parts. I think they ask you to find dot product, find the angle, and then say, are they parallel, perpendicular, or neither? And then 25 is a word problem. Okay, so we'll take a look at that first thing tomorrow. And don't forget the homework is in the packet, not in the book.